Hey, Dr. Amos, here is my engagement table for 741. So the first standard that I chose is analyze data to support the claim that Newton's second law of motion describes the mathematical relationships among the net force on a macroscopic object, its mass, and its acceleration. So this is what we've been building up to over the first couple weeks this semester, Newton's second law of motion, or force equals mass times acceleration. We actually did this lab on Thursday, right before the snow day on Friday. So, what I had students do, I found a online lab for them, and I kind of walked them through how to use it. So basically, what you did is there was a list of cars that you could choose from. So there was like a Tesla and a Porsche and a Lexus and a Honda and a Toyota, etc. And then, so you chose which car you wanted to accelerate, and then a comparable list for deceleration. And then I had them just play around with it for a little bit. And at the end, after they were comfortable, they thought they knew what was going on. I had them make a final graph of a 30-second run with 2 accelerations and 2 decelerations. Then they printed that graph off, and they used the slope of those lines to calculate those different accelerations and decelerations. And then I had them compare their data with a classmate who didn't choose the same cars as them, so that they could start to think about the F equals ma and something that is probably familiar to them. So, modern sports cars like a Tesla or a Porsche use lightweight materials and have really powerful engines, and they accelerate a heck of a lot faster than the 1958 solid steel Ford Edsel that was also a choice in the program. Um, and hopefully that's something that, they kind of intuitively know from driving down the interstate before. Your car accelerates faster than the 18 wheeler because if you rearrange the force equation, acceleration equals force divided by mass. So the ratio of your car's engine force over its mass gives it greater acceleration than the more powerful truck engine, but also the way more massive truck. Uh, and so then I had them write in their notebooks. I had to make a notebook entry in their own words describing this relationship. And then any students who needed modifications, I let them orally explain it, or on their graph, you know, I had them look at the slope of one of their accelerations, and I said, if this line was steeper, would this car have greater acceleration or less acceleration? Or if this line was shallower, would it have greater or less acceleration? Um, the rationale for doing something like this was Hattie's the use of computers is more effective when the student, not the teacher, is in control of the learning. And so this program, it was pretty easy to figure out. They all got it right away. They know how to use computers. So it kind of let them work at their own pace. They could play around with it a bit, choose different types of cars and do trial runs, etc. And then after they played with it for a while and kind of got the hang of it, then they printed it off. So it kind of let them work at their own pace. The second standard is the same as the first, Newton's second law of motion, this time balanced and unbalanced forces. So this is what we will be doing come Monday, weather permitting. So I went to the gym teacher, I found a 2-axis tug of war rope, and I'm going to divide them up into relatively equally sized groups of students, and then have them tug of war. And then I'm going to have a sheet printed off with little squares on it to represent the axis of the two ropes. And they're going to use these squares to draw a free body diagram of the forces based on what happened in the tug of war contest. So if one side clearly won, then there'll be a bigger arrow pointing in that direction, representing a larger magnitude force in that direction. Or if two adjacent sides pulled the other two sides toward them, then there will be an arrow pointing towards the two winning sides, but running kind of 45 degrees down the middle, if that makes sense. And again, um, any students that need to orally explain it, as long as I understand, as long as I know that they understand that there was more force pulling in the winning side, then I'm good. Uh, my rationale for this is high energy as a stimulus for engagement and mild competition. They're a very boisterous group of 15-year-olds, and I think they will really enjoy having bragging rights on whoever gets to win in this little tug of war competition. And then, time permitting, after each contest, I was gonna randomly select one member of each group and have them remove their shoes. So I want them to I want them to see that it wasn't just them pulling on the rope that helped them win the competition. It was also the force of friction acting between their shoes and the ground that was helping. And so, as one person from each group, and then two people, three people, depending on how much time, as they start to lose friction, how does that change the outcome based on how much force they were able to use? The third standard is use mathematical representations to support the claim that the total momentum of a system of objects is conserved when there is no net force on the system. So this will be our introduction to momentum. So they'll learn the equation P equals mass times velocity. They'll learn the units, kilogram meters per second, and the relationship between the rate of change of momentum of a system and net force acting on that system. So for this introduction, I plan on having them do a little reading out of the textbook. So I'll divide them up into groups, and then each initial group will be assigned a portion of the text in a jigsaw setup, and then reconfigure the group so that each new group has at least one expert on each section of the text. And then the reconfigured groups will use their combined knowledge to fill in blanks on a graphic organizer that I will provide them. It'll have sections on net force, inertia, impulse, elastic and inelastic collisions. And the rationale is missing information as a stimulus for engagement and use appropriate pacing. So obviously the blanks to fill in are the missing information to, kind of like to go back to the text and find what they need to fill in any missing information that's on there. And then use appropriate pacing. I feel like the students, as they're in their original groups, will be able to kind of bring each other up to speed on their understanding of it and make sure that they're all kind of on the same page before we move on, and they use their new knowledge to explain to their other group mates and share and kind of build a full understanding of this. The fourth standard is the same as the third standard. This time we'll be looking at conservation of momentum. And so my plan is to do whiteboard practice problems on momentum calculations. I'll put a problem on the Promethean board, and students will complete them on their whiteboards. They'll raise their hands when they're done, and then I will randomly call on one of them to come up to the front and walk us through step by step their process for solving the problem. And then I will give them a momentum worksheet to complete as a homework assignment. So the rationale is worked examples, which Hattie said had an effect size of 0.57 and mild pressure as a stimulus for engagement. So I've noticed sometimes when we do whiteboard practice that it's hard to keep students on task. I will start helping one or two students who need a little bit more support, and then I'll look over and the other half of the room is just doodling on their whiteboard. So I know that I always hated being called on to go up to the front of the class to do stuff, even when I understood what was going on. But I feel like this will kind of keep them a little bit more on task and focused on actually doing the work and understanding it just in case they get called up. Um, and then the homework worksheet, I know it's not exactly a higher order sort of thinking situation, but um, a lot of my students are their biggest struggle academically is they just haven't accepted that now they're in high school that there's an increased academic workload. They aren't used to having to read out of the book and do work on their own. And it's only going to get worse from here on out. So I kind of want to get them used to the fact that, there isn't always going to be somebody there to hold your hand and walk you through step by step. I want them to sort of start to develop a little bit of independence and self-motivation. Then last but not least, design, evaluate, and refine a device that minimizes the force on a macroscopic object during a collision. So this is one of my favorites. It's a classic, the egg drop. So I'll explain to them sort of what they're supposed to do, but basically leave them to their own devices. I'll give them straws and tape and whatever I decide that they're allowed to use for this, and then see if they can design something that will allow them to drop a raw egg from 3 meters and not break. And then I'll break them up into groups. They'll have a little round table brainstorming session to plan and coordinate and build their structure. And then we'll do experimental tests. And if any group's eggs break, then we'll talk about why we thought that happened. I'll let them go back, redesign. If this has to stretch over a couple days, I'm sure it will, but we did a project at the beginning of the semester where I gave them an 8.5 by 11 piece of paper and 12 inches of tape and told them to build the tallest tower they could. And it was incredible to see the creativity and ingenuity that came out of some of them. And even some of my students that struggle to understand kind of the numbers and the equations behind it would design some of the tallest towers. So hopefully this will bring out the same sort of engineering prowess that the tower thing did. And then the rationale for this is mild competition as a stimulus. I think they will really get into it, trying to see, who can drop it from a higher height than 3 meters, or so on. And then also small group learning, an effect size of 0.49, and problem-based learning. So just kind of, I'm not going to tell them, I'm not going to give them very many directions. I'm just going to say, don't let the egg break and see what they come up with. So, all right. I don't have the link posted yet, but I will do that and then I'll get this submitted.